Hey folks, we're going to start doing some circuit analysis today, and that includes talking about Kirchhoffs rules for circuits. So now, if you're in my Physics C class here at LT, there's a packet that you're either going to hopefully have printed out or have a hard copy of, and it starts by looking like this, and there's a lot more pages to it. So it would help if you had that to write on. Otherwise, you can just reproduce the circuits in the notes. It's not a problem. All right. So we talked in the last discussion. We did talk about series and parallel and the properties of series and parallel resistors or parts of a circuit. So, like if things are in series, it's an and. The current will be the same everywhere because the current has to flow through. The voltages will add up, okay, and the resistors add up. If you're in parallel, the voltages are the same. The currents add up. So if you look at these two and look at these two, it's like they're flip-flopped, right? And then for parallel resistors, you do 1 over R to get, you do the inverses to get the total resistance of your circuit. Adding resistors in series increases resistance, adding resistors in parallel decreases it. Now, in order to analyze circuits well, there are two more things that you really have to know, and those are Kirchhoff's rules. And he has two very simple rules, okay? So let's say I had some wires. Okay, let's say here's a wire, and then there's a junction right there, okay, and the wire splits, all right? And let's say I told you that 5 amps of current is going into that junction and 2 amps goes this way. Well, how much has to go down there? Well, you know it's 3 amps. We all know it's 3 amps, right? That's a rule. It's called Kirchhoff's, and it's an interesting spelled name. So there's double H and double F. Kirchhoff's. This is called the junction rule. Okay, and as an actual formula, what it would look like is the net current into a junction is always equal to the net current out. And remember, current is things, it's electrons. So 5 charges go into that little space right there, 5 got to come out. Very much like skiers on a ski slope. 5 skiers ski into this junction, okay, and 2 choose to go down that way. The other 3 have to go this way. There's no other choice to go. The other rule, we kind of talked about that up here actually without actually justifying it. This says that the total current or total voltage of these 3 resistors is equal to the power supply. So what I'm going to do is I'm going to rewrite that diagram just ever so briefly. So let's say we've got a battery and we've got these 3 resistors that are in series, okay? And I'll throw a number on this. Let's say that's 12 volts. Let's say this is a 2 ohm resistor, and this is a 4 ohm resistor, and this is a 6 ohm resistor. All right, well, they were in series, so if you add up the resistors, you get 12 ohms. And so the current that would flow would be 12 divided by 12 would be 1 amp. Okay, so this voltage would be I times R, V equals IR. 1 times 6 is 6 volts, 1 times 4 is 4 volts, and 1 times 2 is 2 volts. Okay, so those are the voltage drops of each resistor. So here's what that looks like. Let's do the ski slope analogy really quick. Let's say you're a skier right there. You're at the bottom of the chairlift. The chairlift raises you 12 feet. Okay, so instead of saying volts, we're going to say feet. Then you go on some level ground for a while, and then boom, you go through run 1 over here, and you drop 6 feet. Okay, if you were at 12 feet and you drop 6 feet, you're at 6 feet left. So we'll call it 6 volts. And then you go through the second run, you drop 4 more feet. Now, if you were at 6 feet and you drop 4 more feet, what are you at? You're at 2 feet. We'll call it 2 volts. And then you're at 2 volts, you drop 2 volts, where are you at? You're at 0 volts, and you're back to the beginning of the battery or the bottom of the chairlift. So instead of saying feet, we have volts in the circuit, but it's the same idea. Remember, volts is like electrical height. And the rule is when you go up, you should always come back down. So the total change in voltage around a circuit should be 0. In other words, if you start at the bottom of the chairlift and you go up and you ski back down to the bottom of the chairlift, your net change in height is 0. Well, same thing for charges marching through a circuit. If they go up 12 volts, they have to eventually go back down 12 volts before they get back to the battery again. So that is called Kirchhoffs, I'll spell that out for us, loop rule. And as an equation, it would look like this. The total, the sum of the change in voltages around any closed loop, that means a complete lap, has to equal 0. So if you go up 12 volts here, you have to go back down 12 volts to get back to the battery. Okay, so we got Kirchhoff's junction rule, and we've got Kirchhoff's loop rule. Now, by the way, Kirchhoff's loop rule, and this is really important to mention, is really a summary of conservation of energy. Okay, so you might remember that electrical power is I times V. So the current is the same everywhere in this circuit. So what we're saying is the power input from the battery is equal to the power output of these three resistors. And power is just work divided by time. So if I multiply that by some time, then I've got the work done by the battery has to equal the work done by the resistors. So really, Kirchhoff's loop rule is an offhand way of writing conservation of energy. Okay. Now, we can use these rules along with these ideas to analyze a lot of circuits, very complicated circuits. So we'll start with this one here. Okay, so if you don't have a copy of this and you need to write it down, go ahead and do that now. Let's go ahead and pause the video. All right, so here's what we're going to do. We're going to figure out the current everywhere and the voltages everywhere, both the voltage drops and also the voltages, the absolute voltages everywhere. Okay, now by the way, for absolute voltage, we always say at the beginning of the battery, we call this 0 volts, and then we call the end of the battery whatever it is, which in this case is 32 volts. Those are the absolute voltages at those two places. Okay, the other places we'll have to figure out. We also, for the sake of argument, we say going through a wire, you don't lose any volts. We're going to assume that resistance of the wires is very low compared to the actual resistances. So the first thing you need to do here is you need to combine resistors. And I look for small amounts to combine at once. So for instance, I look at this circuit, and if I look at R2 and R3, they are in parallel. That's an OR. If I am a charge and I come out of here, okay, I'm going to split up, and I can go through R2 or R3, but then if I go through R2 or R3, I end up at the same spot there. So parallel is an OR, and if you go through one or the other and you end up at the same spot, then they're parallel. So if you recall, adding parallel resistors, we got to do the whole 1 over thing here, right? So what we're going to do is we're going to do that. So the equivalent of just 2 and 3. So we'll say that's 1 over R. That's equal to 1 over R2 plus 1 over R3. And that's 1/12 plus 2/12. That's 3/12. That's 1/4. Flip it over. That R is 4 ohms. Okay. So if we're going to rewrite this now. Okay. So here's that R1 sticking out. That was 4 ohms, right? 4 ohms. This is R2 plus R3, and that's 4 ohms. And then here was R4, and that was 8 ohms. Okay, and then you have your 32 volt battery in this case. Okay, so now these guys, now I'll just scribble that out for now. So we got 3 resistors, 4, 4, and 8, and a 32 volt battery. These 3 guys are now in series. They're AND. If you're an electron and you go through this one, you then have to go through that one and that one to get back to the battery. So these 3 are in series. So series, you just add up. So if I add those up, you get 16 ohms. So our equivalent circuit has a resistance of 16 ohms. So that's an equivalent to all these the network that we had. Okay, then you work your way back through the pictures the opposite way. What current has to flow? Well, that's got to be 2 amps. That's V. You're using V equals IR, right? V is 32, R is 16, I is 2. Okay, so then the key here on these is to use the pictures. Okay, so this current is 2 amps. All right, so then you can figure out the voltage drops. So this voltage drop, and again, I'm just using V equals IR. The 2 times 8 is 16 volts. 2 times 4 is 8 volts. And 2 times 4 is 8 volts. Now, double check. 8 plus 8 plus 16 equals 32. Then I'm going to go up to this picture, okay, and I'm going to transplant those voltages to this picture. So this is an, 16 volt drop. I'll just do that, 16 volt drop. This is an 8 volt drop. Now note on that, the voltage drop for R2 and R3 are both 8. If you're a charge and you choose to go through R2 or R3, you're going to lose 8 volts. You're going to lose 8 volts of height. And then this here is 8 volts. Okay. And then the currents are very simple. The current here all the way to here is 2 amps. Okay. Then it gets to here and it splits. How much current goes up top here through R2? Well, it's 8 divided by 12, which is 2/3. And then how much current goes down here? Well, that's 8 divided by 6, which is 4/3. Now, a quick note, look at Kirchhoffs junction rule. 2 amps goes into this junction, 2 amps better come out. Well, 2/3 plus 4/3 is 6/3, that's 2. Okay, and then same thing here, those two currents meet and become 2 amps again. The last thing is they might ask for the absolute voltage in each spot. So the absolute voltage all the way here is 32. We lose 16, so right there you're at 16 volts. And then we lose 8 more volts through either R2 or R3. So right here, the absolute voltage is 8 volts. And then you lose 8 volts, and of course the absolute voltage there is 0, and you're back to the battery again. I got one more real quick one to do on here. So if you have, by the way, if you're one of my students and you have questions on this, by all means, make sure you ask me. Okay, I went through it kind of quick because it's pretty easy. For part B here, I've got 2 resistors in parallel along with a wire, and it says what's the equivalent resistance of the following circuit. So the REQ is roughly what? 0. Okay, because you have a wire which has a resistance of roughly 0 ohms. and these are parallel, so if you do 1 over 10 plus 1 over 10 plus 1 over 0, you get approximately infinity, and you flip infinity over and you get roughly 0. This would be called a short circuit. What's going to happen is if you were to actually do this and the battery could, a boatload of current would pop out of here. I mean, 20 divided by 0 is a pretty big number, right? Now, a physical real battery can't provide infinite amount of current, but it'll provide as much current as it could. If this were a car battery and you put a jumper cable like this, it could literally melt a jumper cable. That's how much current can flow through that wire. Now, that's a short circuit, okay? We'll talk later on about safety measures to prevent that large current from flowing. The other thing you might see is, what if something breaks? Like, let's say the wire right there breaks, okay? Well, that's an open circuit. And people often confuse the two. So an open circuit means like literally charge cannot flow. There's a broken wire somewhere. Short circuit means too much charge can flow because there's a wire or something with a very low resistance for the charges to get from one end of the battery to the other. All right, I hope you found that video helpful, and thank you very much.